So last time we were talking about the formal description of a DFA. That is that thing with the 5 tuple. It is a reasonable question to ask, why do we need to talk about that at all? Like, the diagram works just fine, and the way that you should think about a DFA is almost always in terms of the diagram. The formal description doesn't really help you to think properly about the DFA. What it helps is for actually making abstract arguments, like if you want to prove something about a DFA, you basically have to use the formal description, because otherwise you're just sort of pointing at the diagram, but that's not a good way to structure an actual proof about something. So I want to give an example of using the formal description to actually do something to prove things about a DFA. That's really the major purpose why we even talk about the formal description. So here is a DFA. I'm going to give names to the states because I am going to describe it formally. I'm going to call the states S0, S1, S2. And the alphabet here is going to be just A. And this is my DFA, all right? Here the alphabet is just A. This DFA accepts. Can anybody say, like in words, what kinds of strings are accepted by this DFA? We've looked at an example like this before, maybe this exact one. It's all A's here. Which strings of A's would be accepted? Yeah.
String divisible by 3.
Yeah, right. If you have a some number of A and the number of A's is divisible by 3. So this DFA accepts any, can I say X in A star? That is to say any string with just A's with length of X divisible by 3. All right, great. We've seen this example before. If you start off, so starting off like from the empty string, that would be accepted. And then in order to get accepted again, you need to take 3 A's at a time, which is why it accepts things which are divisible by 3. But I want to actually prove that. So let's prove this. Using the formal description. If you want to write a real proof, really you have to use the formal description. Otherwise, I can just sort of look at the picture, and I think everybody would believe me that I say something like, well, you start here, which is accepted, so the empty string is accepted. And then any other string that is accepted has to have 1, 2, 3 A's in a row. You believe me because you see my little red dot moving around on the picture, but that's not really a good that's not really a rigorous mathematical argument. So this is the point of the formal description, so that you can actually make real mathematical arguments. Now, depending on your upbringing, maybe the red dot is good enough for you, and I can respect that, I suppose. But you still got to like do the homework and such in this class. So because I'm a mathematician, I care about formal descriptions of things, and I hope that you all care about it at some level also. Anyway. This is what I want to prove. So specifically, I'm going to try and prove this as, can I write like a little theorem here? I mean, it's just this example, but how about I'll just say, let's prove, really to write specifically what I'm trying to prove. The language of this machine, if I call this machine M, I want to show the language of this machine, I'll write it this way, is A to the N such that N equals 0 mod 3. It's going to be convenient to talk about this in terms of the mods. All right, so A to the N, where that is a fancy way of saying the N is divisible by 3. All right, this I want to prove using the formal description. So let's just remind ourselves of what exactly the formal description looks like. We talked about this last time, but here, formally, M is a 5 tuple, Q, sigma, delta, Q0, and F. Where in this particular example, Q is the set of states, which on my diagram are called S0, S1, S2, right? So this is a set, S0, S1, S2, all right? Sigma is the alphabet, which is just A in this example. Delta is a function which is kind of complicated to write down. You really just, if you want to write down what delta is, you have to just list out all of the values. Although in this example, it's not so hard. Because there's only one letter in the alphabet, I just have to say what each of these three values are, right? That's what the three values are. And you look at the picture for this. So the first one says delta of S0. Sorry, that S looks like another delta. It's not. It's a S. Delta of S0 and A. That means, where does the arrow go from state S0? The arrow labeled with the A. You look at the picture. It goes to S1. So this is S1. Delta of S1 and A means, where does the arrow go starting from S1? It goes to S2. And then delta of S2 and A goes to S0 again. All right? So, formally speaking, that's what the delta is. The delta is a function which represents all of the arrows. It contains all the information in all the arrows. All right, Q0. Anybody recall what does Q0 mean? That is the starting state. So in this particular example, Q0 is S0. And F is the set of accepting states. In this example, we have only one accepting state. It is S0. So F is, technically this should be written like this, the set of S0. It should be inside those curly brackets because it's a set. F is always a set of accepting states. All right, so that's the formal description of what M is, the DFA, which I had drawn as the diagram. Actually, its true nature is this bunch of nonsense. And I should write out formally, what does L of M mean? Because this is actually what I care about. This is what I'm trying to prove something about, is the language of M. The language of M, the definition, formally speaking, is all X in sigma star, such that delta star of Q0 comma X is in F. That's the definition of the language of the machine that we talked about last time. Remember, delta star is the same as the delta, only you are allowed to plug a long string into delta star. Now, delta by itself only handles one letter at a time, which is, it's actually more often we are interested in delta star where you plug a whole string into the machine. So this says, if I start in the starting state, Q0, and I read the whole string X, then this should be an element of F. All right. Now, in our particular example, can I just fill in the particular details of our situation? This will say X in A star, right? I'm just plugging in, we already said up here that sigma is A. That is the set containing A. And then over here, delta star, delta star, I'll just have to write it delta star. But Q0 is S0. And when I say is an element of F, F is this set. Being an element of F, actually, there is only one element of F. So this is the same in this case. Being an element of F is the same as just saying this equals S0. All right? That's the set, L of M. And what we want to prove is that that set right there is the same as this, right? This is what I said we were going to prove. So can I just say at this point, I want to show, I'll write sometimes WTS means I want to show. We're not going to do a whole lot of proofs in this class, but every so often. I want to show that this right here, this set here, equals the set X in A star such that, that's not how I wrote it before. I meant A to the N, what? Sorry. A to the N such that N equals 0 mod 3. All right, that's what I want to show. All right. In order to make this happen, somehow we have to rephrase this right here in some way that makes it look like that, right? That's really, I want to show that these two sets are the same. This is the set of all x's which are made up of just a's, which is the same as what I'm saying here. Really comes down to showing that these two things are the same as one another, and that would show that these two sets are the same set. Now, can I say something specific about this up here? one thing that I would like to observe about delta, so we need to somehow describe this function delta star in convenient terms, right? Because I have to somehow make a relationship between this and that. Really, I want to show that this equality, this condition, is the same as this one down here. So in order to do that, I want to describe delta star in some kind of better way. Let's just look at delta first of all. Remember, delta of S0 and A is S1. Delta of S1 and A is S2. And delta of S2 and A is S0. This is what I wrote before. I actually can see some kind of a pattern here. Would you believe me if I said something like, generally speaking, delta of Si and A? If you have S something or other and A, what do you get as the answer to this? Can anyone say there is kind of a pattern here?
Si plus 1.
Yeah, Si plus 1, right? We see S0 becomes S1, S1 becomes S2. Now S2 became S0, which is not really, plus 1 would have been S3. But if I consider these numbers mod 3, then everything works out, right? So I'll just say mod 3, meaning when you see those i's, when I say I plus 1, I mean really I plus 1, but mod 3. So if you go all the way up to 3, you got to roll it back to 0, all right? Okay, I feel pretty good about that. Delta of Si and A is Si plus 1 mod 3. Okay, can I say something about delta star? What about, say, delta star of Si and A? Well, this is the same thing, right? It's, again, Si plus 1 mod 3, of course. Everything I say is going to be mod 3 with the I. It says mod 3 something. Mod 3. How about delta star of Si and A squared? That means I do 2 A's. Starting with Si, I read 2 A's. Can we say what is that going to equal? Any thoughts? Yeah?
Si plus 2.
Yeah, this would be Si plus 2, right? Each time you read an A, it increases that little I by 1 and rolls over if it goes up too high. So if I read 2 A's, that increases it by 2. So this is Si plus 2 mod 3, of course. And in general, I can say delta star of Si and A to the n is Si plus n, reading the subscripts mod 3. All right? And this really is what we're looking for. Because remember I said we want to re-express this in more convenient terms. So can I say, if I start with this, let's say x such that delta star of S0 and x is equal to S0. This is the language of the machine, right? But I can rewrite that thing in the inside the set there. Rather than saying x, I can write this instead as a to the n, because every x in this language is a to the n. And then this will say delta star of S0 and a to the n. I'm just plugging in, instead of x, I write a to the n, because a to the n, because the alphabet is only a's. So in this example, all the x's really are equal to a to the n's. But now, based on what we said before, I can actually simplify this delta star here using the thing that I just scrolled to the top. We know that this is true, right? So this right here, the part on the left, I will simplify as delta star of S0 and AN should equal S sub 0 plus n, right? This is true in general for all the SIs. This will say it's Sn, isn't it? So this says that the string is accepted whenever Sn is the same as S0 when you read the subscripts mod 3. Of course, that just means that n is 0 mod 3. Yes?
Can you explain the mod 3? Is it just because there's 3 states?
Yeah, it's because what I'm saying here is, for instance, when you read a single letter, it increases the state by 1. You go from, when you read a single letter, you go from 0 to 1. or 1 to 2, or 2 to 0. So really it would go 2 to 3, but since I'm saying everything mod 3, the 3 is the same as 0. That's why the mod 3 is necessary. All right, anyway, we're pretty much done here. Can I just say this is the same as a to the n such that n is 0 mod 3, and that's the end. That's what I wanted to end up with, right? So we have shown that the language is what we said all along it was, that it's all the strings of a's which have number of a's is divisible by 3. All right? The end of the proof, I will write shewn. I like to write shewn at the end of a proof because I have an old real analysis textbook, like it's over 100 years old, and that's what they write. They say shew. They have exercises. They say, please shew that whatever, and they tell you, yeah. All right. If you like, you can write shewn at the end of your proofs. You don't have to. Okay. Any questions about that? So this, in my opinion, is the sort of the strength and the beauty of the formal description of a DFA, which in most settings is not particularly useful or beautiful, but when it comes to actually proving things about DFAs, this is the way to do it. Any thoughts about that? All right, excellent. I would like to move on to something a little bit different, although we are going to continue to use the formalism whenever appropriate. We're not usually going to think about DFAs in this hyper-formalized way. We have been talking all along about DFAs and the language accepted by the DFA. Remember, a language which can be accepted by a DFA is called a regular language, right? So a language which can be accepted by DFA is called a regular language. What I would like to talk about for the next couple times is what we call closure properties for regular languages. I would like to think about something like what happens when we combine regular languages. For example, if I want to ask questions like if, say, L1 and L2 are regular, then is, let's say, L1 union L2 regular? This is the kind of thing that I want to ask about. All right? So this is from the point of view of languages as sets, this is a question that you can ask about these sets. If I have two regular languages and take the union, is that still a regular language? You could also think of this in terms of the machines. What this question is asking is, if I have two different DFAs, can I make a DFA which has this language? That is to say, if I have two different DFAs which accept certain strings, can I make a DFA which accepts all the strings accepted by the first two machines separately? In terms of machines, I'm asking some kind of question about, is there a way to start with two machines and combine them together to make a machine which does the union of the two ones that I started with? All right? This is the kind of question. And of course, we could ask about the intersection. So this question means if I have two DFAs which each calculate, different things, is it possible to make a DFA which calculates exactly the things which are computed by the first one and also the second one? All right, that's what the intersection means, the first one and the second one. Can I just say, etc., right? These are thought in terms of machines. These are questions about combining machines together, or they can be thought of as questions about sets here. If I start with two regular languages, is the union regular? Or if I start with two regular languages, is the intersection regular? These are referred to as, these are what the mathematicians, like me, call closure properties. Another way of saying the same, like that first question, if I have two regulars and I take the union, is that regular? Another way to ask that is to say, are regular languages closed under union or intersection? Remember this? I hope you're familiar with this term from math. Closed under. You've seen this like in linear algebra if you've taken that, or other, probably in high school you use this language at some point. Closed under means if I have two things of a certain type and I combine them together, is the answer still of that same type? So if I have two regulars and I combine them with the union, is it still regular language? Or the intersection, or whatever. All right? This is the kind of thing that we want to be talking about. All right. There are a few closure properties that I want to talk about. The first one is the easiest, and it's actually not either of those. The union and the intersection are a little complicated. I mean, they're not super hard, but they will take a bit of doing. The first one is actually fairly easy. Let's talk about closure under complement. The complement is a set theory operation. I hope you remember the complement of a set means all the stuff that's outside of that set. All right, that's what the complement of a set means. So if let's say if L is a language on this alphabet, sigma star, then the complement in our book, the complement is always written with the bar. So L bar means the complement of L, which means all the strings which are not in L. So L is a bunch of stuff. L bar is all the other stuff which is not part of L. So the way I would write this is sigma star minus L. This means all strings not in L. That's the meaning of this is the complement. In this, in our book, they always write the complement using the bar. All right. I want to talk about closure under complement. It is a fact, which I will convince you of within the next few minutes. It's not hard to be convinced. It is a fact that regular languages are closed under complement. That means if you start with a regular language, the complement is also a regular language. All right. So it's a true fact that if L is regular, then L bar is also regular. All right, this is what I want to demonstrate. So the way to think about this in terms of DFAs is if we have a DFA accepting L, can we build a DFA which accepts L bar, right? That would be just, it accepts the opposite. Whatever the original DFA accepts, the other one always does the opposite. It rejects what the first one accepted and accepts what the first one rejected, all right? If we have a DFA accepting L, then can we build a DFA which accepts L bar? This, I think, is something that we have mentioned before. Like, for example, let's just do how about that same example that I was just talking about? This DFA accepts all strings of length which are divisible by 3. So this accepts, let's just call it L. How about a machine for L bar? This, of course, is all a to the n, where n is 0 mod 3. L bar would be a machine for, or it would be the language a to the n where n is not 0 mod 3. That is to say, the string is not divisible by 3. Can anybody say how to do it? There's sort of a simple trick to start with this machine and modify it so that it accepts and rejects the opposite, right? How would you do that? Yeah?
You just change the success state to a regular state, and then you could change the other two.
Yeah, right. You sort of flip-flop every state. If it was accepting, you make it rejecting, and if it was rejecting, you make it accepting. So here is a machine for L bar. it is like this. I am just changing all of the accepting and rejecting states. There it is. This one will accept if the length is not divisible by 3, and it rejects if the length is divisible by 3. All right? That is, you might call this the complement machine, right? The original machine accepts one language. This machine accepts the complement. That's all there is to it. This is a fairly simple trick, and it works just great. Can we say, I think I would like to say this a little bit more formally here. If my original machine is Q, sigma, delta, Q0, and F, with L of M, some language, right? The language that it accepts. Then what is the, can I say which DFA accepts L of M bar, right? That would be the opposite. I would like to write the other DFA in a formal description just in terms of what M says. Can I say it should be, I'll call this one M prime. I want to write the same, in the same way. We're going to have to somehow like change around some of this stuff, right? Can we say very specifically what of the stuff changes and what is the same? Like if you compare these two DFAs, actually they look mostly the same to me. There are some differences, but can we just say, when I'm creating this new machine, M prime, what do I use for the states? Is it the same as the original states? I think it is the same as the original states. So I use Q again, right? How about the alphabet? Same alphabet from before, right? It's still just, A or whatever. How about the delta? This is the transition function which describes what all the arrows are. Is that the same in these two diagrams? I think it is. All right. It looks like everything's the same. How about the next thing? The Q0, that is the starting state. Did I change the starting state? I did not change the starting state. So this new machine has the same starting state. All right, it better be the F that changes. I mean, something's got to change. F is the set of accepting states. I think that actually did change. What is the new set of accepting states here? So in this example, I had this one was the accepting state. And then when I changed the machine around, it became these two that are the accepting state. Actually, there's a very cute way of saying, how did we change the set of accepting states? It used to be F. Can anybody say what is it now? F. It's F bar, isn't it? It's the opposite the states, right? All the states which used to be accepting, that is the F, it's now the opposite, or the complementary set. It is F bar. That's all there is to it, really. I didn't need those parentheses all the way out there. All right. This is the complementary machine. It's almost exactly the same. The only difference is the accepting versus the rejecting states. And now, check it out. Now that we've done this, we might as well demonstrate this. So let's prove that the language of M prime is equal to the language of M, the complement. That's the whole point of this, is that this is a new DFA whose language is the complement of the original one. Can we do that? Actually, it's not difficult, really. The language of M prime. Remember, the definition of the language of a DFA is, it is all x in sigma star such that delta star of Q0 and x is in the set of accepting states. Now, for M prime, the accepting states is this set, F bar. So I'm going to say F bar here. All right? You have to remember the definition of the language of a machine. It's this. It's a little complicated, I guess. It's all strings in the language, or all strings in the alphabet, such that delta star of Q0 and x is an accepting state, which is to say is an element of whatever the set right here is. But I can rewrite this. Check it out. This is the same as, I'm not going to change this business, but just instead of saying is in F bar, that's the same as saying delta star Q0X is not in F, right? Because what it means to be in F bar, that's the complement, that means it's not in F. That's the definition of the complement. This is not in F. What this means is that this is the set of all x such that x is not in the language of M, right? Because this says that x is not in the accepting set of the original machine. So that means that x is not in the language of M. And of course that is L of M bar, right? That is all things which are not in L of M. And there you have it. This new machine that we made, really, its language really is the complement of the original machine. So again, this is sort of the power of the formalism here, is that it allows you to write cute little proofs like this. All right. If you like writing proofs about things, the formalism is your only friend. The diagram is not really very helpful. If you want to imagine that you're a programmer and making diagrams to do useful things, the formalism is not your friend. The diagram is the way to think about it. But we got to do both from time to time. All right? So the moral of the story is, can I just reiterate? So can I write this? I'll write it as a theorem just so that we have it written in big letters in your notes. If L is regular, then L bar is regular. Right? This is another way of saying this is regular languages are closed under complements. You can remember that slogan, and you should also remember how exactly you do it. It's very simple. You swap the accepting and rejecting states. All right? Regular languages are closed under complements. That was the easy one. I said that we're going to start off with a simple sort of machine construction. I want to talk, we got 17 minutes remaining. We can start talking about unions and intersections. Let's talk about intersections first. So what about intersection of two regular languages? I will tell you, regular languages are closed under intersections. I'll write this as a theorem, although we're not going to get to the proof just yet. First, I'll tell you how to build the machine, and then maybe we'll do the proof next time. So this says if L1 and L2 are regular, then L1 intersect L2 is regular. All right. I don't want to do the proof of this theorem just yet. I want to give you the idea of how do you build the new machine. So what this means is if I start with two different DFAs, there was a way to create some kind of mother DFA which represents both of them and accepts strings only which are accepted on the first one and also the second one. That's what the intersection means. Let's see if we can, I'll give you the basic idea of the construction here. Let's say I have two DFAs or two regular languages. How about one is this, a to the n where n is even, and then L2 is a to the n where n is divisible by 3. I'm just taking simple examples just so that we know what they look like. This one, I'm going to try and draw these two DFAs. And I'm going to give names to the states. So in the first example, I have just evens and odds, right? And A goes back and forth. This is an example that we've seen many times before. So I will call this M1, right? And then I have M2 is the machine for the second one, and that's the one that we've been talking about this same example all day. It goes like this. Right? Here is accepting state. And these ones, I should have written this rather than squeezing it in. I'm going to say 0 mod 3. I'm going to write this again. They're too small. These represent 0 mod 3, 1 mod 3, and 2 mod 3. This is the meaning of those states. And I have arrows going around in a circle. And that's the starting state, and this is accepting. Okay, those are my two DFAs. My goal is to combine them together into a monster DFA which somehow does both things at the same time, all right? And there is a simple way to do this, at least theoretically simple. I mean, it might take a few minutes to actually work it out, but the simple way to do this is create a new machine where the states in the new machine are pairs from M1 and M2. The idea is I want to create a new machine which does both of those machines at the same time, sort of in parallel. And so the states of my new machine will look like pairs of states from the original machine. It's going to look like the starting state will be even and also 0 mod 3. That's the first pair of states that it could be. All right? I'm thinking of all the different ways that you could have a state from up here together with a state from down here. So one way is that it's even and also 0 mod 3, or it could be odd and also 0 mod 3. And then it could be, there's going to be 6 of them, just because I'm making pairs from 2 things and also 3 things. Even and 1 mod 3. And it could be even and, odd and 1 mod 3. And it could be even and 2 mod 3. And it could be odd and 2 mod 3. Right? These are the 6 states in my new machine, which is meant to do the 2 machines sort of simultaneously. All right? And now, where do I put the arrows? The arrows on my new diagram go according to where the original arrows went. So, for example, in even and 0 mod 3, where does the A go? You look at where does the A take the even. The even goes to odd when I do A, and the 0 mod 3 goes to 1 mod 3. So you just do both of those things in the pair. So the even becomes odd, and the 0 mod 3 becomes a 1 mod 3. That means the proper arrow is here. All right, even and 0 mod 3, you look at what happens to the even. Up here, it becomes the odd, so I went to odd. And what happens to the 0 mod 3? It becomes the 1 mod 3. So I went to this one. All right, you have to find, oh, sorry, I got to escape. I saw puzzled looks on your faces because I didn't scroll it. All right, you look at what happens to each part of the pair, and that's where you make the arrow go to. Okay, what about even and 1 mod 3? Somebody want to say, where should this one go to? You ask yourself, where does each of these 2 go to, and that's where you make it go. Yeah.
2 mod 3.
Yeah, odd, even becomes odd, and then the 1 mod 3 becomes a 2 mod 3 in the other diagram. So that's like this. All right. And then even and 2 mod 3, unfortunately, I'm going to have to cross the arrows over. This one should go over here, right? The even becomes odd, and the 2 mod 3 goes to the 0 mod 3. That's this arrow right here. So this one here goes like that. I don't like crossing the arrows, but sometimes you got to do it. I suppose I could have gone around the outside, but not into that. All right. What else? You know, we got to fill in all the arrows. So there have to be arrows from down here. Odd and 0 mod 3. The odd becomes even, and the 0 mod 3 becomes a 1 mod 3. So this should go up to here. That's like this, all right? The odd and the 1 mod 3 becomes an even and a 2 mod 3. That's this. And then the odd and the 2 mod 3 also has to go across. Maybe I'll go around the outside for that one, like that. Odd becomes even, and 2 mod 3 becomes 0 mod 3. All right. This is the DFA, which you get by doing both machines at the same time. All right. Now we should say this is not quite done. We should say where is the starting state? Well, how do you where you start here just depends on where you started in these 2 things. I start in even and I start in 0 mod 3. That's right here. So I start in this state, which corresponds to the pair of the two starting states. So that's my starting state. And what is the accepting state, or states, as the case may be? Now, here is the important thing. This is where the intersection comes into play, right? Come on. I'm looking for the intersection of the two languages. That means I want to consider only things which are accepted here and also accepted here. So I'm going to look for all the pairs which are accepted on both machines. There's only one of those. That would be even and 0 mod 3. That's this one. All right, this is the only one which is a pair which represents things which are accepted on both parts of the pair. All right, so this one is going to be the accepting state in this machine. All right. So I'm going to try and say in words how we did all of that. So you make pairs of states. You connect arrows, or according to where each part of the pair goes. Like when I wanted to know where does the arrow go from even and 1 mod 3, I look on one diagram to see where the arrow went from even, and I look on the other diagram to see where the arrow went from 1 mod 3, and that's where I put the arrow in this big machine. All right, you connect the arrows. The starting state is the pair of starting states, the pair of the original starting states. And then what's the accepting state or states? It is the set of all states which are which are pairs of accepting in the first one and also accepting in the second one. That's because I'm looking for the intersection of the languages. So I have to use the word and there. So the accepting states are all where both parts of the pair are accepting. The first one is accepting and the second one is accepting. This is because we're looking for the intersection. So the first one is accepting and also the second one is accepting. All right, can we just try another example here? We got a few minutes. I would like to do another example of combining together two DFAs into a bigger machine. Can I say, actually, there's a name for this procedure to combine them together into this big machine? This is called the product construction. Product is the word I'm using because you make pairs. This is actually corresponding with the Cartesian product of two sets. Remember, like a set A cross B, it means all the set of all pairs, where the first thing comes from the first thing and the second thing comes from the second thing. That's what we're doing here. This new machine is somehow the product of these two machines. That's the way to think about it in terms of set theory. All right, we got 5 minutes. Let's do one more example. How about, this one will be a little more interesting because I got A's and B's here. Let's say the first language is AX, where X is in AB star. So remember, this means all strings beginning with A, but they might have B's after the first A. And then L2 is going to be all strings, let's say X in AB star, such that X uses an even number of B's, and I don't care about the A's. All right. These are my two languages. I would like to draw a DFA which accepts the intersection. So first of all, I should write a machine for each of these two just to begin with. And now these two languages, I believe we've talked about these examples before. L1, I'll call this M1. This is going to be the machine for the first one. It accepts only if it begins with A. So If your string begins with A, then there should be sort of a permanent accepting state like that. And if it begins with B, it's a rejecting state. So this is the first one. If the string starts with an A, then it's automatically accepted no matter what happens after that. And if it starts with a B, it's automatically rejected no matter what happens after that. Okay, now I'm going to give these states names. I'll just call them like ABC because I'm about to make some big thing with pairs and I want to label them so that it all makes sense. All right, and then M2, I'll try and write over here. Even number of B's. This is, you can do this with two states, and I'll call these ones S and T. And the B's go back and forth. This is like evens and odds for B's. And the A's just don't matter at all. That means I'm going to put A's looping back to themselves. All right? These are similar to some of the things you did on the homework. And we talked about similar things last week in class anyway. Okay, so these are my two original machines. Let's try to create the product machine from these. Now, here's a little pro tip. I'm actually not going to start off by writing down all the states. Actually, in this example, there are going to be 6 total pairs that you could make. There's, A, S, B, S, C, S, and then A, T, B, T, and C, T, right? But actually, it's a little easier. I'm just going to say start with the starting state, and then draw the diagram from there. You'll see what I mean. Because it turns out in many of these examples, you don't actually need to use all of the states that you get from all of the pairs. There are 6 total pairs that you could make here. But actually, some of those states you can never actually get to in the diagram. So you will save yourself a little bit of effort if you just start off with the starting state, which is A, S. All right, this is my first state. That's the starting state. And I'm just going to, from there, I'm just going to see where the arrows take me. So can anybody say, where should the arrow go if I do A from the state A, S? What you should be looking at is, where does the A go up here? And also, where does the A go over here? And you do both of those things. Somebody, maybe someone I haven't heard from yet today? What do you think? Yeah? B and T, she says. You will look at, where does the A go when you do A? It goes to B, so it's going to be B. And where does the S go when you do A? I think back to S. Yeah, so actually it goes to BS. All right? AS goes to BS. Oh, sorry. I turned my iPad off. Talking about BS. Like that. Okay? All right, what about from AS, the B? Maybe I'll, someone else want to tell me? From AS, what if you read the letter B? Where does it go to then? You think, where does the A go? And also, where does the B go? I mean, where does the A go? Also, where does the S go? What do you say?
CT.
CT, yeah, I agree. A goes to C with a B, and also S goes to T with a B. So this goes to, I'll put this down here, and hopefully I won't have to cross the arrows. Actually, I did this example ahead of time. I guarantee I will not have to cross the arrows, unless I messed it up on my paper. All right. Now, we're not done yet because we need to continue, like, for instance, this BS needs to have 2 outgoing arrows. There has to be an A and a B. So what happens at BS? Sorry, it's about time to go. When I look at B, S, and I read A, B stays as a B, and S stays as a S. So actually, this one is like that. Because when I'm at B and I see an A, it stays as a B, and S also stays as a S. What about B? When I read letter B, B stays like it is, S becomes T. So this, when I read a B, becomes BT, like so. All right? Let's just fill in the rest of these. BT, when I read A, B stays a B, T stays a T. So this is like that. BT, when I read a B, B stays a B, T goes back to S. So this becomes BS, which goes back like that. All right, I'm almost done here. I have to, I'm done with this one because I already have 2 outgoing arrows. Also done with this one. I need 2 outgoing arrows here. CT. The C, let's read A first. C stays as a C, T stays as a T. All right. So this is like that with an A. And with a B, C stays as a C, T becomes S. This goes to CS. All right, unfortunately, I do have to make arrows from CT now. All right, with an A, CT, C stays like it is, T stays like it is. So this is like so. And with a B, the C stays like it is, the T becomes a S. This goes back like that.
Can we combine those, the two CT states?
Oh, I wrote it wrong. Sorry. This should say CS over here. Yeah, that
CS.
would not make sense. All right. I know we're out of time, but can we just say what's the accepting state here? It's the pair which is made of accepting states in both of the original diagrams.
Yes.
BS is the accepting state. And that's the end. Notice I only had to write 5 states, not all 6 of them. Saved a little effort.